good morning, good afternoon, and good evening. I'm Guangqi Chen from Kyushu University, Japan, the organizer of the forum. We have invited 30 keynote lecturers to introduce the latest scientific research progress and achievements. Today, we are pleased to welcome Professor Hatzor as a secondary keynote lecturer. Thank you very much for him to join us in his busy schedule, especially for so early. Also, I have invited Professor Ma to chair today's keynote lecture. Now, Professor Ma, would you please to make a brief self-introduction and then start the lecture? Thank you a lot.
Okay, thanks, Professor Chen. Good morning, good afternoon, good evening, everyone. It's my honor to chair Professor Hatzor's keynote lecture. Actually, it's really very happy. I'm very happy to chair this lecture. I didn't see Professor Hatzor for many years. I think it's longer than 5 years. So I'm happy to see him here and hear his lecture. Professor Hatzor is our longtime friend. He is currently a professor of Ben Gurion University of the Negev, honorary president of ICADD16 Commission, and the founding president of ISR National Group of Israel. He focuses on research of rock mechanics and geotechnical engineering, rock slope and underground cavern stability, block theory, DDA, and friction of rock discontinuities. He has received many national and international awards, including the American Rock Mechanics Association, ARMOR Applied Rock Mechanics Award, the Shamsha Prakash Foundation Award for excellent
recording in progress
in practice, for significant contribution at the Israel Mineral Science and Engineering Association Award. Professor Hatzor have made great contribution to the innovative research of geological engineering. Actually, we are now under a big shock of COVID, and hopefully the COVID will over very soon. And we hope Professor Hatzor to come to visit us in the near future. And for this lecture, please take part in the discussion with chat. If anybody have a question, please write in the chat. And you can input the questions and comments in chat window anytime during the lecture. And we will ask the lecturer, ask Professor Hatzor, answer them one by one in order. And if the time is sufficient, a voice chat is also acceptable after typing questions and comments. Okay, Professor Hatzor, please.
So maybe, thank you very much, Gue, for the nice introduction. So maybe I can now share my screen, if you let me.
Okay, so probably I need to stop the sharing.
Oh, okay. Now I can share my screen. Okay, and here we are. So can you see this?
Okay, no problem.
Yeah. Okay, so thank you very much, Professor Chen, for the invitation. It's a big honor for me to do this. And indeed, I haven't been to China for a long time, I think from 2018. So it's been a long time since COVID. Hopefully, we can meet again after COVID. So I prepared a talk that explains the Well, this is part of ICADD, and ICADD is all about DDA and discontinuous deformation. But this talk will go more into the basics of friction. You know that friction is a fundamental property that governs the deformation of discontinuous media. And this is why it's important to explore friction as deeply as possible. Of course, the geophysical and seismological societies, they are interested in friction with respect to earthquakes, but we are interested in friction also for landslides or for stability of underground openings. And as you all know, there is a very important role that roughness plays in friction. And roughness is not implemented so much in DDA. And maybe after this talk, I can convince you to consider modifying your use of DDA for inclusion of roughness roughness geometry. Now, the roughness of the joints is very important in the beginning to determine the peak friction, but it also evolves with displacement. So there are two challenges. One, to model the roughness that contributes to the friction of the interface at the peak friction before sliding starts. And then the other challenge is to model correctly the degradation of the roughness through shear. And what are the parameters that control this degradation? So this is what I want to explore in this lecture. And then I will move on to a case study that some of you may have already seen. The work is mainly, the first part of the talk, this part, is mainly experimental, based on experiments from our lab. And in these experiments, we try to see what are the factors that influence roughness degradation through shear. So that the first part is really experimental. And the second part of the talk is a case study, a very famous case study of the Vaillant landslide, and how by implementing roughness degradation, we can model this slide correctly. So let's begin. So for some of you, this will be a review of well-known concepts. I just want to draw a line and to make a common denominator between all of us. So to determine friction in the lab, there are several methods we can use. One is the simple direct shear device. Simple, I mean simple, not simple shear, but direct shear, simple device. And this is, it has a lot of advantages, because when we use direct shear, we can model correctly the deformation across the roughness. Because if we apply constant normal stress, for example, then while the upper box is shearing, it can also dilate up and down. And that dilation plays a very important role in the shear process. So direct shear, the advantage is that we can model dilation. We can apply significant normal stresses. We can use significant blocks, significant size of blocks, up to 10 centimeters or so in a standard configuration. The drawbacks are that it's very difficult to model pore pressure, and the stress condition is not constant through shear. The principal stresses rotate once we start shearing, because initially this is a principal plane with no shear, and then once shear starts, this becomes this no longer is principal plane, and so the principal stresses rotate. So we don't keep the stresses constant through shear. And we're limited with the velocity. You can't go too far and too fast, because then we're losing the alignment. We want those normal stresses to be as much as possible evenly distributed across the interface. And so if we go too far, we lose alignment, and moments begin to come in to play a role, and we lose the homogeneous distribution of normal stresses. So there is a constraint on the amount of displacement and the velocity. The double shear system has been very popular in the 70s and 80s and 60s, mainly by Professor Dietrich, who established the rate and state laws. He used that kind of device. So those are also relatively static tests, low velocities, can apply very high pressures here. But again, you're limited. Usually it's not done to monitor pore pressure, and you're limited with the velocity and the displacement, the amount of displacement that you can apply. But the advantage over the direct shear is that we have homogeneous normal stress distribution across the interface, if this is important. The disadvantage is that you cannot model dilation across rough joints. When we move on to torsion, torsion is now becoming very, very popular, although it has been in the literature for many, many years. So the advantage of the torsion test is that we can go very fast, up to meters per second, and we can go very far, tens of meters of shear. So if we want to model a landslide and what happens to the interface through shear, then and to model rapid shear and long distance, then the torsion could be a good solution. And finally, there is our classical triaxial shear test, where we can introduce a discontinuity here. And again, to go back to torsion for a minute, this is another, as in the case of double shear, and also in the triaxial less, but in the double shear also, we don't normally monitor dilation with torsion. Triaxial shear, you can monitor dilation, as you well know, of the entire sample when it shears. However, from the radial strains, but when you have a discontinuity and you shear it, it's more difficult to monitor the dilation. The advantages of the triaxial system is that you have a very well stress field applied on the cylinder and on the joint. By simple stress transformation, we can find the normal shear stress here. We can control pore pressures, and we can go to very high stresses. The disadvantage is that we're limited to the amount of displacement we can model, because again, if we displace too much across this interface, then the alignment is violated, and people have devised those spherical seats to address that. to allow for more displacement. But in practice, the amount of displacement we can apply in triaxial shear is limited. So what we're using in this research is our direct shear system. It was manufactured by a company called TerraTech. They no longer exist. They were bought by Schlumberger. And so now it's embedded within Schlumberger. This is Bob Griffin, the mechanical engineer from TerraTech, who even after they have been purchased by Schlumberger, he still continues to come to Ben Gurion University and provide service. And so these are some graduate students that you will see their results in a minute. And so we have a normal piston of up to 100 tons force and a shear piston of 30 tons force. And those, so everything is in servo control, both the normal and the shear, both in load and both in load and displacement control. So we can impose a normal stress, constant normal stress, and monitor the dilation by the output of these 4 LVDTs very accurately, while pushing from the shear piston. And then we can control the shear piston also by load or displacement. We can shear under a constant displacement rate or under a constant load rate, depending on the application. So in the triaxial system, we started out with this system also by TerraTech a long time ago when I came to BGU. I did my PhD at Berkeley and with Professor Goodman, and then I came to BGU in the early 90s and received a grant to buy this system. So this is my old triaxial system. And now recently we received another grant and purchased this new triaxial system, we call it, from Vinci Technologies. It's a subsidiary of Vinci Technologies called Flux Lab in France, in Paris. And the nice thing that is completely different technology. These are working on syringe pumps here. We have 3 pumps for the axial piston, for the radial pressure, and for the pore pressure, and they're very, very accurate. The drawback is that the syringe pumps, because of the small volume, they cannot really follow the post-peak deformation very well as in this triaxial system. Even if the system is stiff, as you see, it's very stiff. It's got wide columns. Still, if you want to monitor or to study post-peak deformation, this system I find is much more reliable. That works on a hydraulic power supply that applies the piston. Here with these syringe pumps, it's very good for the controlling of the pore pressure and the confining pressure, very, very accurate. However, to follow the system, to follow the axial stress all the way to post-peak, I find it very challenging in this system. So we are working on this to improve it. So how do we bring the discontinuity to the lab? So this is a method proposed by Goodman. You can drill across it, or if you intercept the joint in the borehole, is fine, and you can then cast it and then bring it to the lab, or we can just bring the blocks like you see here. This block, this interface here, see. We put it in the shear boxes, the upper and lower shear boxes. So we basically reconstruct the situation in the field. Now, if you notice this, I just want to see if there's no chat, no questions. Oh, okay. Sorry, let me just make room for the chat on the other screen. Here it is. Okay. All right. Chat. Okay.
Ah,
good. Yeah,
Professor Hatzor, You will answer the question at the end of your lecture.
Okay,
They
good.
can input the questions anytime, but
Mm.
you don't need to answer them.
Okay, thank you. Thank you for the clarification, Professor Chen. So, so you see that when you go to the field, the discontinuity is not smooth. It's very rough. And also it has some filling material. And all these things need to be considered when testing the friction. So just to show you one example, this is the same material that you saw in the slide before. This is in the triaxial shear, and this is in the direct shear. And very interesting that the triaxial shear gives us this failure envelope, whereas the direct shear gives us this failure envelope with peak friction here is 41 degrees and residual friction here is 23 degrees. This is just for the geologists when they are not used to friction angle. So what happened? How come the friction coefficient is so high here with respect to this? Well, this is simply because when we shear the rough interface, we mobilize the roughness, and that the mobilization of the roughness provides much more shear resistance. Whereas when we shear this surface, so-cut surface, even if it's filled with crushed dolomites from this previous slide, still we're not mobilizing any roughness apart from the roughness of the so-cut. And this is why we end up with a much shallower failure envelope and almost half of the friction. So it's very important to realize how important it is to consider roughness. So just a brief review of the literature. Some of you will find that not necessary, but still, I don't know the audience and who's sitting in the audience. And so I just want to give a broad but brief introduction of the principle. So it's interesting to note that even if you know this material, the direction that I'm taking this is maybe different. Excuse me. I don't have COVID, but a little bit cold. So if you consider this, consider Byerly law. All the geophysicists and seismologists talk about Byerly law. Byerly law. He compiled results from many labs, also from his lab. Some of it pre-existing discontinuity, some of it solid cylinder, and plotted and got a line. He went to geophysical stresses up to 20 kilobars, right? This is 20 times 10 to the 3. So these are kilobars, 20 kilobars. So it's very high. And so he obtained a linear failure envelope, and you see, this is the criterion. So basically what he's saying that the crust of the earth has a cohesion of 0.5 kilobar, and then times 0.6 normal stress. So the friction coefficient of the earth crust is somewhat like 0.6. However, when we go to the low normal stress area, we see that we lose the cohesive intercept, like in rock mechanics, and we see that the friction is higher, 0.85. I don't know what explanation, or if he gave a good explanation for this, but for those of you who are familiar with the rock mechanics literature, you know that the Patton's law, that is a bilinear law, it predicts that at low normal stresses, we're mobilizing the pure friction plus the dilation angle, and in high normal stresses, we are using the residual friction. So Patton, because he also found this bilinear criterion, introduced the dilation angle to explain it. And the dilation angle is simply the inclination of these sawtooth, saw teeth above the intermediate plane, the medium plane. And it's very easy to see from this force polygon that the dilation angle is a net contribution to the pure friction of the plane, and therefore this is correct. This is correct. The friction is actually the pure friction plus the dilation angle, and up above some normal stress here, we are losing that, and we are getting the cohesion plus the residual friction. So if Patton's rationale is correct, this is what I want to suggest, then we can say that the dilation is important more or less up to a normal stress of 2 kilobars, right? That 200 MPa. So that could be the motivation for our work, because people may say, oh no, but dilation is also only important for very low normal stresses. Or say, no, why, if that is so, why did Byerly find this bilinear law? So there has to be a contribution to the dilation even at lower normal stresses, and up to where? Up to about 2 kilobars. So it's actually quite significant also for geological purposes. So this is what I'm proposing. So, so how to measure dilation and roughness? And Nick Rangers, in his PhD thesis, came up with a very novel method. First of all, he used this dial indicator and plotted it on a tracing paper, as you do with a profilometer, but he also did it with these, you see, those circular plates to which he attached the Brunton compass. And then he showed, these are the poles, for those of you who are familiar with stereographic projection, these are the poles of the small plate, and these are the poles of the large plate. You see that the poles of the small plate cover much more area than the large plate, meaning that the small plate can capture the roughness better than the large plate. So we understand from this, that the roughness is scale dependent. It depends on scale. It must depend on the scale of the measurement device. If it's a line, so the length, the wavelength of the measurement, right? And if it's a sphere, if it's a plate, then the radius of the plate. And this is very easy to understand, because the smallest the radius of the plate, the more you can measure the details of the roughness. So the roughness now becomes a scale-dependent parameter, not just I, as Patton proposed, but I per scale, for some scale. And another thing that Ranger did was to show, he showed very nicely, that if you have an initial roughness and you shear, so the amount of dilation you can expect to get goes down with the distance of shearing. So if we only shear 1L, we get this delta H1. If we shear 2L, we get this dilation delta H2. And if for every L we plot all the values, this is 1L, this is 2L, this is 3L, this is all the values, and take the extreme values at each base distance, we get a roughness envelope that goes down, meaning that the actual roughness angle is reduced with displacement for a given roughness profile. And then, of course, as Goodman suggested, you can put it into the shear criterion, phi residual plus I, the relevant dilation for the amount of displacement we're talking about. So for each amount of displacement, there's going to be a different dilation angle. And that's very important to realize two things. One, that the dilation is scale dependent, the roughness is scale dependent, and that the dilation changes with displacement. Another contribution that we will use in the case study was by Bandis, who later collaborated with Barton. So in his PhD thesis, he showed, and you all know this chart, he showed that the peak friction of peak shear resistance changes with the block size. So again, if the block is small, 60 millimeters in this model across the same joint roughness, if the block is small, we're mobilizing the maximum amount of shear. And with increasing block size, we are mobilizing less and less and less shear. And that goes back to what Rangers showed us, that if the block is small, it rides over all the asperities and it mobilizes all the roughness. And this is why we're getting a much higher frictional resistance than when the block is high. And just to point out something very interesting, note that the peak friction is mobilized when you shear approximately a distance of 1% of the block length of the overriding block, more or less. So 0.6 millimeters for a block of 60 millimeters and 3.6 millimeters for a block of 360 millimeters. It's just a rule of thumb. He never said this. He and Barton, they never said this, but it's something that comes out from this nice test, the set of tests, that about when you shear about 1% of the overriding block length, you're mobilizing most of the friction. And finally, Barton proposed, he used the same result, that the shear strength is comprised of the residual friction angle, and then a geometrical component, and then an asperity failure component, and that's what led to Barton's JRC. But the understanding that we have a basic friction angle for joints, which is the pure friction angle. What it is, we need to determine. And then the geometrical components and the strength failure component change with size. So the smallest blocks will give us the highest geometrical and shear strength components. Okay, so we know all that. And now we go to the real world. And in the real world, people have been studying this for a long time, starting from the 80s when Mandelbrot proposed his fractal theory. People wanted to see if it works also for faults, and they started plotting the wavelength and the roughness. This is in terms of power spectral density, and the units here are meter cube, but you can also think about it as in terms of RMS, deviation from the mean, and to look the same. In any case, what we see that if we plot those on the log-log plot, we get a linear trend. Meaning that the roughness increases with the wavelength. The larger the wavelength, the higher the roughness. So now, as we already saw before in the historical overview, the roughness, you can't talk about the constant value of roughness. You must consider the scale of the measurement. And it goes like this. And this has been shown for 9 decades of wavelength. It continues to plot on a straight line. So how can we create a rough faults in the lab? Well, what we do, we take a prism. This is a limestone prism. And we are moving aside the direct shear system, and we're using just the normal piston. We use the normal piston. The direct shear system is here on the side. We move it aside. We have air bearings here. We open up the air pressure and we can shift it to the side. And now we tell the piston, the piston to go down at a constant rate, not constant force, but a constant velocity rate. And we create a configuration of 4-point beams. So we have 1, 2, 3, 4, 4-point beams. So the axis, so the compression arch is like this, and here it is tension. So now I take my T, and exactly when I take my T, it breaks. Always breaks when I take my T. So we get this fracture. So this is basically a tensile fracture. This is a tensile fracture that we created in the lab. And the roughness is very significant. This is a diabase or gabbro taken from China, from a quarry in China. And you can see this, we found it in Israel, but it was originally from China. And you see this roughness was created in this method. Then we can go and saw cut the surface. We get the roughness of the saw cut. And then we can go and polish the surface. So we get the polished roughness, the polished roughness. And then we need to scan the roughness. So there's different ways we can do it. This machine, this profilometer, we used most of our tests, our measurements were done on this profilometer. It was good to go all the way down from fractured to saw cut surfaces. For the polished surfaces, we went to another university, to the Hebrew University, to use a white light interferometer, and because it can avoid the reflections. It can deal with the reflections that come back from a very, very smooth interface. And finally, in our lab, we have another young faculty member, Yuval Tal, and he has this scanner that is very, very accurate. And we can, here you see, we use it now to study the roughness of inclined joints for induced seismicity studies, how roughness influences induced seismicity, and simply you see the device, how it works. And so we have all these tools to measure the roughness. So we can do that. So when we do that, we see and we plot it in the space of length and RMS. RMS is more intuitive. Excuse me. So the RMS is more intuitive, but it's the same physics, the same geometry. You see that the fractured surfaces, fracture A, fracture B, fracture C, they all follow a fractal geometry. And that's clear because they're natural, they're not machined. Once you machine the surface, you saw cut the surface, then it's going to stay fractal up to a point. And that point would be the roughness of the asperities. From that point onwards, it's going to stay flat. And of course, so it's not going to be fractal, no reason, because it's machined. And the polished will be flat from the beginning, because it's very, very smooth. And just to show you the profiles, you can see here, this is the fractured, this is the fractured B, this is the saw cut. Oh, no. This is another fracture. This is the saw cut, and these are the two polished. You can see that here. These are the two polished, and this is the saw cut. You see what is wide distribution of roughness profiles we can get in the lab. So we can go from, these are 0.1 or so microns, and this is 1,300 microns. So very, very large. So of course, when you do this, when you say what is the RMS, now we know that you have to say this RMS is for some kind of length. We did it for the 4 centimeter range. So RMS, again, it's a function of the length. and we do it, in this case, we report it for 4 centimeters. Okay? So now, how does the result look like? And look at how the results you get for the front. This is the same rock, the same diabase from China. And you see for the very rough interface, fracture A, we get a friction coefficient of more than 2. And then it breaks and it slides, and here there's some stick slips. And then this is fracture B and C. This is the socket. They all converge more or less to the same residual friction of 0.6 as we're used to. But when we go to the polished surfaces, we see that the friction coefficient goes much less. Even this is around 0.1 or 0.2, very, very low. And one of the interesting things of this research is to show that the stick slip oscillations that indicate unstable sliding are very much a function of roughness. So if we take these areas here, stick slips from here and from here, you see that the amplitude of the stick slip peaks at the socket surfaces, and then it goes down to both extremes. Somehow the socket surface is more prone to stick slip deformation than the other surfaces, and you can see the stick slip here. This is in time space. This is the displacement. You see that the socket is much more pronounced, and we'll get back to that later. So what happens to the roughness with shear? So as we would expect from Ranger studies, the roughness would degrade with shear. So here we start with 7 millimeter slip and increase to 12, 10, and 15. And you see that the roughness profile or the roughness spectra are reduced in all cases, and they are reduced more with increasing displacement. So it's interesting to show that it's reduced on all scales, on all lengths. Simply the surface becomes smoother. So this we can show very clearly. About normal stress, it's not so simple. With the normal stress, we're getting a trend where below 5 MPa, we're getting the smoothing. So this is the ratio before and after. It's lower than 1, it gets smoother. However, when we go beyond 5 MPa, these are limestone interfaces. Of course, this would be different for every kind of surface. So when we go above 5 MPa normal stress, the surface, in fact, becomes more rough. It's not so easy to explain why this is so, but the observation is good. For example, look here. This is 5 MPa normal stress. And you see that those asperities are decapitated, they are cut, they're sheared through. Whereas when we go to 12.5 MPa, you see the opposite. We get a rougher, this is smooth. And here oops, I'm sorry, how did that happen? No, that's not from me. What's that? That somebody is drawing. Okay, never mind.
Please don't drop on the screen.
Yeah. So in this case, in the higher normal stress, we get roughening. Why is that happening? I think we have a suggestion. We're just working on it now. If we consider the shear stiffness of the interface, this is the shear stiffness of the interface. We find that the shear stiffness of the interface increases with normal stress. And so it's possible that under higher normal stresses, the asperity material behaves more brittle, in a more brittle fashion. And so it's being plucked and leaves a rougher trace after the deformation because it's stiffer. This is just a hypothesis. We haven't worked on it enough. Only now my student, Doron Morad, is going back to near-body tests and trying to make sense. But this is where we are at this point regarding normal stress. Now about the stick slips. Let's go back to the stick slips. So this is from Jagger and Cook, now Zimmerman also. So this is very famous. The stick slip is unstable, sliding. We have a maximum and minimum. This is assumed to be the static friction, dynamic friction. You can see it for granite, you see it for gabbro, the static and the dynamic. And this is the model. Some of you may be familiar with it, the spring slider model. You push, you absorb elastic energy up to a certain point, then it jumps. And that would be the displacement versus time function. Okay, so in Jagger and books, all the equations are there. All the differential equations are in the book. And you can calculate everything. And then what we're finding in this research is that the stick slip for a given surface, same material, is very much a function of roughness. And another thing that is important to realize that the stiffness of the machine is a very important parameter in the stick slip deformation cycle. So it's very important to be able to measure the stiffness of the machine correctly. So if this is a sketch of our system, this is the piston, this is the K machine, and this is the block that is sliding, we can measure the stiffness of the machine in two ways. One, this is the displacement of the piston, and this is the displacement of the LVDTs here. So in between is the machine. So the difference between these two displacements would be the curve on which we can find the stiffness of the machine. So that's one way. The other way is just to take those slopes. Those slopes are by definition, if you go back to the theory, those slopes are the stiffness of the machine. And you can see they all plot on a very, very nice line. So when we combine the two methods of measuring the stiffness, either by subtracting the piston displacement from the block displacement, or from taking the instantaneous stress drops here, this is those slopes. In both cases, we get, so we call it reloading, and unloading. We get more or less the same value and represents the stiffness of the machine. So we know what the stiffness of the machine. This is Km. We know exactly what it is. Say 10 to the 5th newtons per millimeter. Now, another thing that is important to see is that the amplitude of the stick slips is also a function of the control mode. If we are controlling from here, we prescribe constant piston displacement rate, then we're getting these curves, the gray shade for two roughnesses, the 7 millimeter and the 500 millimeter. Again, the 7 millimeter is more noisy than the 500 millimeters. However, if we control from the block, we tell the block to go at a constant rate from the output of those LVDTs, then we get this noisy, this jerky motion. And that's because each time the system releases the energy and the block flies forward, because the command is on the LVDTs, it's being retracted to correct for the spontaneous jump forward. And this is why we're getting those oscillations that are much, much higher. And therefore, and you can see that in both cases, we used exactly the same surfaces. So there's not a surface effect. So this means that the control mode is very important. And in fact, in order for all the theory in Jagger and Brooks Cook to work, the command, the control is to be on the piston, not on the block. So all the equations for the spring slider and all the theory is developed when this is proceeding in a constant velocity. So we call it the PD symbol. That's another point. And finally, we want to look at the dilation. We see that the dilation is very strong in the socket interface. You see that this is the stress drop in brown, and this is the dilation in gray. And you see that it's in phase. These are the stick slip oscillations of the socket, and this is the dilation. So the dilation goes up and down with the stick slip. This doesn't happen when we look at the fracture. You see, this is the stress drop. This is the stiffness of the machine. This is the stress drop, and the dilation is not. There's no dilation. There is a global dilation of the interface through shear, but during the stick slip oscillations, there's no dilation. And of course, the same with the smooth polished surfaces. We don't see anything. There's not even stick slips here. So what we see that the stick slip deformation is very much dilatant. It's a dilatant process, and that's important if we want to study, for example, induced seismicity and things like that, and the interface is dilating through shear. Then, of course, the pore pressure regime is also changing through shear, and this has to be taken into consideration. So just to show you an illustration, what's going on, this is the roughness ratio before and after, you see. So the socket, we stay on 1 before and after, but the fracture is being sheared, and therefore the roughness ratio is lower than 1. And you can see it also graphically before and after. And the simple mechanistic just illustration is that the rougher interfaces are being sheared, the asperities are being sheared through, whereas the socket, and these are experimental results. These curves here are real experimental results. We see that the socket, or maybe this is just a cartoon showing the experimental results I showed you. I don't remember if it's 1-to-1 or it's just a concept. But we saw it before, and so in the socket there is a dilation. So that without shear, so we see that the stick slip oscillations, that is the analog for earthquakes and unstable sliding, is very much a dilated process, and it's very much sensitive to this roughness of the interface. And if we look at all of our results, we see this trend. This is the RMS at 4 millimeter. And you see that for the socket, we have the highest stress drop. The stress drops are the boxes. And the stiffness of the machine, by the way, is those X's. It's the same all through the spectrum of the wavelengths, okay? So of course it does. So the roughness doesn't influence. The stiffness of the machine. However, a very important thing to realize is that the shear stiffness, the circles, is dependent on the roughness. So we call it the Ki. Ki, we call it the shear stiffness within the stick slip cycles. So it's an initial slope here. And you see that this initial slope Ki is not constant. It's much higher for the noisy, for the socket, for the one that oscillates strongly, and it goes down to both ends. So now we realize that the shear stiffness is also a function of roughness, and that gives us a rationale for the results, because if you consider the classic plot, it's not by Schultz. I mean, this was proposed by Ruina and Rice when they discussed Dietrich, when they discussed the rate and state. But they came up with this idea, everybody in the seismology literature is very familiar with this, that the interface has some kind of a critical stiffness Kc. And now when the system wants to do this, this is the K of the system, sorry, let me take it back. This is the stiffness of the system K. The interface of the system. The interface, this is the stiffness. This is the post-peak slope. So the condition for instability is that Kc, the critical stiffness, is higher than the stiffness of the machine. Now, the problem with this idea is that it cannot be measured. you cannot measure KC, because when you're at point B and the interface wants to go to point C along this path, you must go by your stiffness. You cannot make any other route. It has to go on this slope. This is why the system cannot see this curve. So in the theory of rate and state, they have equations. If they take the A and B and DC, then they can find analytically KC. They can write from DC, A and B, they can write an expression for KC. But note that you cannot measure it in the lab. And now what I'm saying here is that the instability, which is basically the amplitude of the delta tau, is higher when the difference between Ki and Kc and Ki, which is a proxy to Kc, and K is the maximum, is the highest. So this would be the most unstable, because in this case, the stiffness of the interface is much higher than the stiffness of the machine, and therefore we can expect a much higher oscillations. And when we go to the extremes, to the very rough and to the very smooth, the difference between the stiffness of the interface and the machine is very small. And because it's small, it's more stable. So this gives us the rational explanation to this observation. So I will be, I see that we lost Professor Magu. Yeah, he liked it. He liked what I'm saying. Okay, so now we are ready for, and the final thing is the influence of velocity. And you see that for initially rough surfaces, in this case, it's saw cut against the surface grinder. When the surface is rougher, the change in velocity is less dramatic, whereas when the surface is smoother. And probably this is because when the surface is rougher, those barriers to motion, the asperities, prohibit the system to slip, and we're getting a less significant velocity weakening. You see, here we increase from 1 micron per second to 100 microns per second, and very little effect on the friction. Whereas here, we only, and these are the smoother ones, we only we increase from 0.4 to 1 to 10, and look what a dramatic, you can see it here. You see, so this is the friction coefficient for the rough. Rough in this case is the saw cut. And this is for the smooth. You see how it falls with velocity? So the velocity effect or slip weakening is very much sensitive to the roughness. So this is the experimental background I wanted to show you. Now, Professor Chen, can we take a 2 minutes break before I continue?
Okay, as you like.
Yeah, so give me just 2 minutes and we continue, okay?
Okay, you can restart. And please input your questions if you have in the chat, and then I'll ask you to ask your questions to the presentation lecture, and you can discussion directly. And I will use the chat order to let you ask questions. 我先用中文跟大家说一下，如果大家有要提问的话，可以先在这一个 chat 里头把你的问题提出来， 然后呢，我到时候会根据那个提问的先后，请大家自己念一下，然后直接跟那个讲演者进行对话这个讨论。谢谢大家。Hello.
Yeah, I'm back. Okay. So thank you for waiting. Sorry.
Yeah, no problem. Yeah.
This cold started this morning. I got up with this cold. I don't think it's COVID, but I did catch a cold somehow. So now I can understand everybody that is at home with COVID. So now in the time that we have, I want to, this took longer than I expected, but I'm not, I don't regret it. Because I think we're covering very important things. And so now I just want to show you a case study where we can try with DDA to model the friction degradation. So this is the famous case of Vaillant slide. And you probably know about it. It was 1963, and in a few seconds, the mountain collapsed and overtopped the dam. Overtopped the dam and by a wave of about 250 meters. And then this wave swept into the valley, and more 2,500 people lost their lives. And this is the mountain after the slide. So what happened? What happened? So these are some photos from Life magazine. You can find them in the internet. And you see, the dam didn't collapse. The dam stayed intact. But this is the valley where it happened. No, this is the canyon where it happened inside. This is the valley where the flood flooded the town with 2,500 people dead. Very, very bad. What happened? So if we look at the cross sections, Semanza is the son of the structural engineer who built the dam, and he's an engineering geologist, and he drew these maps before and after this slide. So it's here. This is the Vaillant Gorge. This is the slide. This is the dam. It's here in northern Italy. Here. So here, northern Italy here. So you see, the thing is that it was already a slide. It was an old slide. This already slid in the past and stopped here. But it slid on the past because we see some parts of this material juxtaposed on this slope. So we know that there was a landslide in the past, and then erosion through the landslide, and then the valley, and now the slide started again, once again. So what happened? So if you look at the groundwater regime, this is the caustic mountain, and we're getting water, and we have a water table. Now, each time you draw water, the water table goes down. Each time you add water, the water table goes up. So we have water pressures for sure. This is the seat, this chair shape slope. Now what's going on? So this is the precipitation over time. Now, the electrical company of Italy wanted to create power. It's I don't remember if it was 100 megawatt or 200 megawatt turbine in this dam. They want to make power. So in order to make power, they need the reservoir level to be high. But when they increase the level of the reservoir, they get movement. So they dewater, they take water out, and the movement stops. Okay, if the movement stops, they raise the level again, but then the movement starts again. Here, see? The movement starts again. If the movement starts again, they draw the water. They draw the water, the movement stops. Now, throughout this process, Semenza is telling them what you're doing is dangerous because the mountain is moving and responding to the changes in water pressure. And Professor Leopold Muller, that we give his award in the rock mechanics ISRM, Leopold Muller Award, right? So he was a very, very famous rock engineer, maybe one of the leaders in the world. Yeah, I think he started rock mechanics and rock engineering, the journal. So he's a consultant, and he says, no, it's okay. You can go ahead. As long as we drain it, they drill the drainage tunnel. He says, go ahead, it's fine. But here's what happened. So after, when this was stopped, they raised the reservoir again, and then the slide ran out. This is the run out of the slide. And this is the water level in the piezometers, you see. So everything was monitored, and they could have avoided it if they practiced more carefully. And then it led to this catastrophe. So because I told you that the dam stayed intact, you understand that the error or the problem here is not the structural engineers, but the engineering geologists. They are at fault. This is where the slide took place on this hiatus here. It's a limestone with some clay on top. I was there. They invited me to give a lecture, also keynote lecture, when they celebrated or commemorated 50 years for the Voyant. It was in 2013. I gave them a talk about DDA. I didn't do all this back then. I showed them other things. They were interested in DDA. So they took us to see this. And so what they appointed the investigating committee with Hendren and Patton, two very famous rock engineers from the US. And they came up, Hendren and Patton came up with these conclusions, that the clay layer is somehow the friction between 5 and 16. And it's in a residual state. So the residual state is 12 degrees. And the rock mass, this is the friction angle assumed for the rock joints, and it's not degraded at all. So these are the initial conditions, let's say, that Hendren and Patton took for their analysis. Then they did their analysis, very elaborate analytical analysis. In the report, in the report you can track that. And this is the result. The result, it's shown in a space of velocity and distance, depending if you degrade the clay by 50 or 60%, you move from this circle to this circle. I mean, this map, it's the velocity distance map. So, and that explains the failure, because we know how far it slid, we just don't know how fast. But there are other models, hydrodynamic models, that gives you some constraints on the velocity in order to raise a wave of 250 meters. So this is the result of Hendren and Patton. They did this analytical procedure, which I will not review here, but it's basically an analytical approach. And of course, over the years, many authors try to deal with this and solve it in different ways. Here's what we did, very, very simple. We said the rock mass is 40 degrees. And the clay layer initially is 22 degrees. We say 22 because we know that under these conditions, it's marginally stable. The degraded parameter is 12, as in Patton and Andron. And then through slip, we're only going to degrade 25% in the rock mass from 40 to 30 and from 12 to 9 in the clay layer. And the degradation will be a simple model building on the result I showed you by Bandis, that when you displace 1% of block length, you mobilize maximum shear. So for every block, once it moved 1% of its length, the friction at the contact is reduced from 12 to 9 in the clay layer. And then it remains on 9. So 1% block size. And the friction in the joints is reduced after 1% of sliding from 40 to 30. So we basically followed their concept, but used much less degradation and in a very simple way. So, so this is the DDA model with 4 measurement points or 5 measurement points along the basal plane and 4 measurement points in the center of the slide, right? So we basically took the data from the report regarding the orientation of the joints and spacing. And we reproduced the slope that we reported in Semenza's work. So we're modeling this section. So this is before the slide and this is after the slide. So this is before the slide. So here's what it looks like. The slide begins to slide and the velocities begin to evolve. So the red colors is velocities that are higher than 15 meters per second. You see these points here are very fast. Now everything is fast. Everything is fast. And now these blocks here begin to slow down because they have to climb on the slope. So they slow down. This is still very fast. And this continues to push up. And remember, we have constraints from the field, so we can always know what's going on in the field if it's following the physical reality in the field. And now you see it stops. The velocity is gradually stopping, and that's where I stopped the movie. In a few minutes, this will all stop. Oops, sorry. So, if these are the results of Patton and Hendron for 50 and 60% degradation, these are the DDA results for the simple bilinear law with 25% degradation. So we don't need to degrade the friction to such low values, only 25% to reach those same results. And just an interesting point to point out, if you look at the velocity maps on this cross section 1, 2, 3, 4, 5, or A, B, C, D, you see that point 1 is here, is going furthest away. It's traveling the longest distance, and it reaches the highest velocity. And the other points are less. Whereas in the center of the in the center of the mass, everything slides coherently together. Yeah. So this is the distribution of the velocities within the slide if you're looking longitudinal or transverse. Now, my friend Giulio Di Toro contacted me after the paper was published and asked why we didn't use his results. And it's true, he's right. He had torsion and double shear and triaxial results for the clay that we're studying. The reason I'm ashamed and embarrassed to admit that I was not aware of their study. It was published in JGR, and we were not aware. So we took his results. We took this curve. This curve is for the clay, going see different velocities. This is for torsion. This is in a 1.3 meters per second, less than the side, but still very. Oops, sorry. I have to fix that. And we implemented it in the DDA code. So for the clay layer, we took this scenario. So the clay layer, the degradations follows this exponential decay with displacement. Depending if this distance is 25 meters or 20 meters, so we did both. And this is for the rock mass, we kept it as it is in our model. So these are the results. This is the bilinear, our model, which is the simplest. And of course, with the exponential, it's a bit going a bit faster, yeah. And this is depending on the distance to steady state, if it's 20 or 25. So this is for 20, this is 25. But by and large, I guess we can say that the results are not all that much different. So this is a very crude, this is a very crude and simple bilinear law. And this is and this is just based on empirical results from literature. And this is actual experimental results from the lab. The results are about the same. And so the conclusions, the roughness degradation increases with sliding distance under relatively low normal stress. Under higher normal stresses, depending on the interface material, roughness may increase with sliding. We saw that roughness controls the magnitude of stick slip oscillations when steady state conditions are retained. We showed that stick slip oscillations are strongly dilatant, and we found a critical roughness below and above of which sliding is stable. We showed you that the velocity weakening is more characteristic of initially smooth surfaces, and rougher surfaces don't exhibit so much velocity weakening. A roughness degradation does control the velocity and the total distance of the slide runout, as we demonstrated using the Voyant. Now, the back-analyzed minimum friction coefficient was 0.16 for the Voyant. This is in agreement with the experimental results of the Toro. Therefore, here's my suggestion. I say we can use DDA. Some people here are great experts, like Professor Chen and Gao Feng, my friend. These people and Professor Ma that left the meeting, they are experts. They can use, and many of you that I don't know personally or don't recognize the names right now, but you can use DDA for back analysis of slides and then come up with the friction degradation scenario, or at least with the minimum friction. And this is interesting because you cannot do it in the lab. You cannot shear in a lab to distances of hundreds of meters and velocities of tens of meters per second. You cannot do this in the lab. So if you have a strong numerical tool like DDA, you can back analyze the landslides and come up with friction degradation scenarios and minimum friction. The most important thing, however, I want to point out, that is against the Toro. He said, the Toro, in one of his classic papers, I think in Nature, with Professor Tullis, they said that friction drops down to 0. And I don't accept it. I showed you that in very conservative estimates of friction degradation, the friction did not drop to 0. There is a lower limit. For here we get the 0.16 friction coefficient that does not go lower than that. And this is without incorporating pressurization, vaporization. Maybe Professor Sulem discussed phase changes. I don't know I don't remember, I didn't see what was his topic, but he studied phase changes in the limestone to show how that, without all these things, just a simple bilinear degradation, where we can explain the failure without needing to go down to friction coefficients that are lower than 0.16. This is my conclusions, and thank you very much for listening. These are my colleagues, Amir Sagif from the Geological Survey that helped me with the roughness measurements, Juan Pablo Ibanez is in Argentina, the winners of the World Cup. He did the implementation of the bilinear degradation in DDA, and Yuval Tal consulted us, and then used some numerical analysis that I didn't show you for the critical roughness study. And these are my graduate students: Omer Biran, Guy Davidesco, Nir Badet, and Doron Murad. And thank you very much for listening, and I will be happy to accept some questions.
Okay, thank you very much for your excellent lecture. Because Professor Ma has not come back. As you mentioned in your conclusions, we can use DDA to make a back analysis, especially for the friction angle. We use round to get in agreement with each other, the real round. Then we can get friction. Can you, how about your opinion? Can you use in the experiment to show the back analyze the friction in agreement with you experiment, or there's much difference? Did you have any experience for that?
I didn't. This is the only case I studied with using the mapping of the slide by Semanza.
Yeah.
And then we checked the initial conditions of the friction proposed by Hendren and Patton. We checked them in DDA, so we know with DDA when it's stable, when it's beginning to slide. So it's just from the DDA, and then we studied different degradation scenarios. But I never did it on a different slope or compared to my own friction studies. What I'm saying is that because we know this slide went to a distance of hundreds of meters in velocities of tens of meters, we cannot reproduce this in the lab.
I see.
So if we back analyze it for the geometry, we want to start from initial geometry, get to the end of the geometry, and if some constraints, for example, here, the height of the wave gives you a constraint on the peak velocity, and the mapping gives you a constraint on the distance. Then it can be used to understand what happened in the interface.
I see. Maybe we should try a little more about that.
It's interesting.
Yeah, I'd like to confirm that you should leave at 3:30 exactly, or a little bit later. No,
maybe
since
a few
we have
minutes is okay. Maybe a few minutes is fine.
Few minutes, and then please you determine it's time for you leave. Okay. If you want to stop right now, you can stop right now. Okay. And we have questions from the chat. The user ID is Jin Yao Gao. Please use mic to ask your questions.
Oh, okay. Can you hear me, Professor?
Yeah. Yes. Okay. No problem.
Okay. I'm the doctoral student from Kyushu University, and it's my great honor to
which university?
Kyushu University. Doctoral.
Kyushu?
Yes. Professor Chen's club.
Yeah, my student.
Okay. From Japan.
It is my great honor to listen to your lecture. I have one question. How to consider the cutoff of the asperities in the experiment during sharing? Because some researchers suggested that the asperities under higher normal stress will be cut off in a more horizontal angle, and which means the fracture under higher normal stress turns to be smoother after sharing. Thank you.
That's an excellent question. So the best way to do this would be to scan the interface after shearing with a method, with a computer program that allows you to calculate the angles of the asperities and to study the change in the slopes of the angles. So some people are working on this now. It's not like our roughness measurements, because they are like only vertical XYZ, but there are image processing programs that let you study the distribution of the angles on the interface. And then you can see if indeed what happened. You have to take it out after the test and then scan it again and see the change in the angles.
So does that mean the mechanical behavior during shearing test is only sliping of between the asperity sliping?
It depends. So I showed you in the lecture that for the socket surfaces, the dilation was without any damage to the asperities. No damage, just up and down.
Oh, okay.
But when we were, and this is under 5 MPa normal stress, but when we went to the very rough fractured surfaces, then when it sheared, it sheared through, it did not dilate. So if it's going to dilate with no damage or shear through with a lot of damage, it really depends, for a given normal stress, it really depends on the level of roughness. Of course, we start all the tests when the interfaces are completely mating configuration. The one mating, meaning there's no gaps, and then we shear. So we find that the dilation with no damage is only characteristic to the socket roughness. I don't know if this answers your question.
Okay.
Okay, thank you. Thank you,
you.
Professor.
Okay, thank you for your question. Is there any other questions? Please raise your hand or you just use your mic. Okay, Professor Wang Gonghui from Kyoto University. Please.
Can you hear me?
Yeah, okay, no problem.
Okay, thank you. Thank you very much, Professor. I sent the chat to you, ask you the question. My question is, you show the different shear behavior and the different normal stresses. So do you think the high normal stress will affect the true contact area and then influence the shear resistance? I mean, you have the different shear behavior. So do you think this kind of different shear behaviors result from the, the true contact area or not?
Yeah, I think absolutely. There are studies, classic studies, showing how the contact area changes with normal stress. And so certainly the contact area will be part of that, yeah. You need to use a transparent material like MPBA, and then you can actually record the change in contact area under normal stress. And there's no doubt that under higher normal stress we get higher contact area, and that will affect the shear resistance. But how the change in contact area influences the observation that we see that the roughness increases with normal stress, I'm not sure yet. I don't have a mechanistic explanation for that yet. What I know, what I showed you, is that the stiffness of the interface increases with normal stress. That could relate to the contact area, but I need to look into it more.
Okay, thank you very much. May I have another question?
Sure.
For the Velt Dam landslide. So did you think about the rate effect of the sliding surface? I mean, the clay material, you give the permanent value for the flexion angle. So sometimes this kind of flexion angle is also rate dependent. So in your simulation, did you think about this kind of?
Yeah, so you can try to implement rate dependency. We did not model it. I know that people in the DDA community started, I think Professor Chen did something about that. Anyways, I think, yeah, people in the DDA community did try to implement rate and state into DDA. We did not do it in this case. What happens is that because you are just degrading the friction angle, you get the velocity weakening by itself. You don't need to impose another criterion for the velocity weakening, because once you degrade the friction, the slide accelerates anyhow. So I don't need to impose, in addition to the friction degradation of the asperities, I don't need to impose another weakening parameter. That's what I find. It's enough that you can do it this way or that way. You can assume a steady state condition of a constant friction like in rate and state studies, and then apply A and B, A minus B, and see how velocity weakening. But in our case, we do differently. We just shear the asperities to a certain amount after a certain amount of displacement, and then the slide runs without imposing a velocity weakening model. Then we tried the other way. We tried the Toro's results, where he showed the weakening. If you remember in the lecture, he showed, I think you still see this, Ken. So he showed those different tests. But these are not velocity, this is not rate and state tests. These are, each test was done at a constant velocity. So it's not like a velocity, it's more like the test I showed you from my lab, this test. All of them, each test, all those tests are done at the same velocity. It's not a velocity weakening test. And then you see how the friction coefficient is affected by the velocity. So that's what Dito did in his tests. He did this. So it's not letting the slide accelerate, it's just checking the reduction in friction when imposing different velocities. So we were able to implement this law into the DDA. We just reduced the friction along this exponential curve with displacement to a minimum after displacement of 20 or 25 meters. That's from his lab tests from here, see?
Mm-hmm. Mm-hmm. Okay.
And then we let that run in DDA. So the velocity evolution of the slide is a result of this friction degradation.
Okay. Thank you very much. Anyways, I say you are simulation has good result with the real fact. Okay. Okay. Thank you very much. Yeah.
Thank you, Professor Wang. Professor Wang Gonghui is a professor of Kyoto University, Japan. He is also an expert on experiments. Thank you for your discussion. From this picture, it seems distance dependent. Friction is distance dependent. Someone will have some knowledge about velocity dependence friction. Is that?
Yeah.
Do you have any data for that? Velocity dependent. And Professor Wang has do some high-speed landslide and for some equivocation and maybe it's forget the friction change very much. We need such kind of experiment data to support our DDA analysis. Up to now, we have there's no very much for this kind of data.
Yeah, I agree. I think this is where we should go in this direction. My slide keeps changing. We need to study this more. I think we need to study more the two end members. One is changing the friction value with displacement because of processes like degradation, and the other is just changing the friction because of the velocity. These are two different approaches. I'm saying that the velocity in the real world, in the lab, you control the velocity.
Okay.
But in the real world, I'm saying that the velocity is a result of the friction degradation. So in the physical world, it's a different process than in the lab.
Mm-hmm.
The velocity evolves through sliding.
Mm-hmm.
So you have to give it a reason. So of course, people have studied the pressurization. We're not talking about all that.
Mm-hmm. I see.
So this just shows you that if you change the friction a little bit, you can get those velocity, and then of course the slide accelerates just by the physics of the sliding without need to implement a velocity weakening model.
Okay. Professor Hatzor, there is a question raised from chat. Do you have time to answer that?
I will take just this one, and then I must go for another meeting. I'm
okay,
sorry.
this is the last one. The user ID is Qi Chen Zi. Please ask your questions, please.
I can read it. Chi, do you want to read your question, or shall I read it?
Dear Professor Yossi Hanser, thank you very
Please
much
introduce.
for your
Please
wonderful.
introduce yourself at first. Please introduce yourself at first.
Thank you very much for your wonderful presentation. My question is, you found the critical reference.
Excuse me. Please
yourself.
introduce yourself at first.
I'm a professor from Beijing University of Architecture and Civil Engineering.
Okay, thank you.
My question is, you find a critical reference for instability.
Right.
Is this condition necessary or sufficient condition for the instability? Thank you.
Good. So there traditionally people talk about two criteria for instability. Number one is velocity weakening, and number two is stiffness, Kc greater than K machine. Okay, is this clear? Yeah, you're familiar with that. So we go back. Let me go back. Just here, this one. Good. So two criteria for velocity for traditionally, one is velocity weakening, and the other is this condition that Kc is. So your question is the critical roughness.
Yeah.
Is basically a new concept now. And I think your question is excellent. And I don't want to say that everything that has been done before is wrong, but certainly this has to exist. This criterion proposed by Dietrich, Ruina, Jim Rice must exist for instability. What I'm showing you in my work is that this instability, the difference between Kc and K, is a function of roughness. And I don't need the criterion for velocity weakening. Don't know if this answers your question.
Okay. Okay.
Is that
So
okay?
So it's a new idea that this is a new idea. Nobody talked about this before. Let me tell you, I think that this is maybe my most important work until now. And I don't know if it will be realized. It will be realized in the profession or not. This is why I sent it to this journal, because I want the seismologists and geophysicists to realize this. That I think all of the rock mechanics studies done in the seismological and geophysical geologists, they all did on SOCAT. So they all were here. But the reality I showed you before, 9 decades of wavelength, the reality of the faults is on all of the spectra. And then this behavior will not be observed. So that is the main impact of this study. This is definitely correct. Nobody can argue about that. The condition for Kc greater than K. This has to exist for instability. But then how much instability is really what I'm proposing? I don't dare to declare it the way you asked, but I think this is what comes out from this work, is that the degree of instability is a function of the roughness.
thank
Is that
you.
okay? Okay.
Is this okay?
Thank you very much for your discussion. 10 minutes past you.
I hope
the time.
this was my answers were sufficient. And if not, people are welcome to contact me by email, and I can discuss more.
Okay, maybe we have a chance, and the next year you should come to China for ICADD16. Also,
it depends on the corona.
Maybe I will invite you to China next year. Maybe I will come back to China.
Oh, that would be wonderful.
And invite you to do experiment together.
That would be wonderful.
Okay? Yeah. Do you remember we worked in Wuhan and talk about things? Yeah.
We're talking about. We already met. I remind you, in Professor Shigenwa house in 1992.
Yeah, that's
when
right.
We met sitting on the floor.
Yeah.
And I never forget. And then in Wuhan. So sure. Yao Yoyong, you didn't have any question?
No, very good. Your presentation is great.
Moving away from DDA to the lab.
Maybe,
I'm more comfortable in the lab.
Chinese Lunar New Year, you can visit us.
When?
Professor Shi is very keen to visit Wuhan. They missed us, and we also missed him. We also missed you. We look forward to your visit in the very near future.
Yeah, I'll be happy to come if you invite me.
Wuhan is also Professor Chen's hometown.
I know. I think he has I think he still has an apartment there.
Yeah.
Yeah, it would be very nice to meet again, all of us, I always have good memories from the ICADD meetings in the past.
Yeah, maybe I'm sorry, Miss Professor Ma haven't come back. Maybe we'll say goodbye for you since it's too late. I don't want to keep you so long.
So thank you very much for listening. Professor Wang, hello. So, hello. So I enjoyed it very much, and hopefully next year we can meet in person and continue talking about these intriguing concepts of friction.
Yeah, that's right.
Okay. So bye-bye, everybody. Thank you very much.
Bye-bye.
Indeed.
Okay. Yeah, thank you everyone for your participation. Thank you, Professor Hatzor. And we will meet you next tomorrow. Tomorrow we'll have another lectures given by Professor Tohata from Japan.
Okay.
And Professor Wang Gonghui will be chair the lecture.
Okay, thank you.
Okay, thank you. Thank you all of you to participate.